Lesson 6.1, the standard normal distribution. Describe the characteristics of a standard normal distribution. Find the probability of some range of z-values in a standard normal distribution, and find the z-scores corresponding to the regions under the curve representing a standard normal distribution. That's the objectives of Lesson 6.1. There's three properties of the standard normal distribution. One, it is bell-shaped. Two, the mean is at 0. And 3, the standard deviation is at 1. Now here's the formula, the density curve, f of x equals, and then so on. We're not really going to have to do it, but this is the formula that they use to make this graph here. And let me show you here. We've got right here, this is our mean, and it equals 0. Our mean equals 0. It's been standardized, okay? And then over here, about right in there, and then over here, and it's not. This would be 1, and this would be -1, and this is mu minus sigma, or 1 sigma, and this is mu plus sigma, okay? Now, remember, this is right in the middle, so 50% of the data is over here, and 50% of the data is over here, all right? If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, and it can be described by the equation above, by this equation right here, we say it has a normal distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. I'll show you more about that in just a second. Some properties. The area under the graph of a continuous probability distribution is equal to 1. There is a correspondence between area and probabilities. So probabilities can be found by identifying the corresponding areas in the graph using the formula for the area of a rectangle. Area equals height times width. Okay? This is important stuff. Kind of got to commit it to memory so you'll understand. Example. During certain periods at the JFK airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes as illustrated. Okay, so this is what they're talking about, the rectangle right here. Okay, it's uniform. Now, given that the uniform distribution, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. And I want to show you something here. All right. This right here, this is the area, and this area, well, the area of this is 0.2, because 0.2 times 1 is 0.2. And this area here has an area of 0.2 as well. 0.2, okay? 2 minus 1 is 1. 1 times 0.2 is 0.2. And so on and so on. Okay? So this right here has an area of 0.2. This right here has an area of, I'm off. I'm still off a little bit. That has an area of 0.2. So all of these have an area of 0.2. Well, if you add them up, that equals 0.2 plus 0. That equals 1.0. Okay, so the entire area of this is 1. Now remember, probability of x is somewhere between 0 and 1. Okay, the probability of something. 0, it never will happen. 1, it most definitely will happen. And then the gray area is in between there. All right, so our question was, has a waiting time of at least 2 minutes. So that's going to be the probability that x is greater than or equal to 2. All right, so let's find that area there. And let's see here. We're going to say that's from here to here. All right, and so we just have to add those up. 0.2 plus 0.2 plus 0.2, and that equals 0.6. So there's a 0.6 chance, or a probability of 0.6, that a randomly selected passenger will have a waiting time of at least 2 minutes. Okay? There we go. Standard normal distribution is a normal distribution with the parameters of mu equals 0 and sigma equals 1. The total area under the density curve is equal to 1. So all this area here, all of it, all of that area there, and it goes on like that, all of that area equals 1. Okay? Now that being said, what do we know? What do we know? Well, here in the middle, this is mu. This is mu, and it equals 0, okay? So 50% of the data is over here, and 50% of the data is over there, okay? So z is greater than -1. Well, where's -1 at? -1's about right in here. All right, that's -1, -1. And we're wanting to find greater than -1. So we're wanting to find all this area over here. Okay? All this area over here. Now, to do that, there's 2 ways. One is a table, and the other is one is a table, and the other is technology. All right. So let me see here. And I'm not sure why, but this changed, and that was supposed to give me my thing staying right there. And then my table. Where'd my table go? There it is. All right, so I want to find -0.1. So if you look across here, that's after the decimal, and down the side is before. All right, so we want to find -1.0, and that is right here, -1.0. That's 0.1587. All right. -1. Now, this -1.587 is right here, or this 0.1587 is because this table here reads from the left to the right. Okay, so this is 0.1. So to find this area here, remember the entire thing is 1. So we're going to say 1 minus 0.1587 and 1 minus 0.1587. That's going to give us 0.8413. So this area over here is 0.8413. 0.8413. That's terrible penmanship, isn't it? 0.8413. All right, so that's this area over here. Now let's see if we can find the second one. Clean up my mess a little bit. And so we've got negative 2.5. So about 1 is here, about 2 is right there. So 2.5, we're going to say negative 2.5. So we're wanting the area less. We're wanting this area right here that's less than. Okay? So let's go back. Let's go negative 2.5. And that's going to be right there, 0.0062. So this area here is 0.0062. So there's our answer, 0.0062. Now, what I haven't showed you yet is the calculator, and I'm going to redo all of these after I do these three here. Okay. Now we already know. Let's see here. We already know this next one here. Negative one. We found it a little bit ago. Negative 1, and it said this entire area here was 0.1587. Okay, so to find this right here, to find this area right here, to find that area right there, we're gonna take this number here equals 0.1587, and we're gonna subtract this little area right here, 0.0062, and that will give us our area for this right here. And this is using the table. And we've got 0.1587 minus 0.0062, and that's 0.1525. 0.1525. Okay. Now, here's the thing about the table. It rounds. Okay. It does some round. So the technology will be a little bit different. That'll be due to rounding. So let's find this one here. Okay, it's greater than 0.1 or greater than -1. So we go in here, menu 552. Our lower bound is -1. Our upper bound is positive infinity. So we'll go 999. Press enter, and we get 0.8413. 0.8, well, that's what we got last time, right? All right, now let's find less than -2.5. So menu 552, our lower bound is going to be negative infinity. Our upper bound is going to be -2.5. And then we press enter, and we got 0.00621. Okay, that's very, very close to what the table gave us. Very close. Now let's find this. Let's find the third one. And we have menu 552. We got a lower bound of -2.5, an upper bound of -1, and we press OK. 0.152446. 0.152446. So just, off a little bit. Okay, just off a little bit. The table is off just a little bit. All right. So we got that. Now sometimes we might be given the area, so we want to find 95%. Okay, so over here somewhere, and this is 95% of the area. We want to find all of this right here, but we don't know what the Z number is. We got to find that. Okay, so to do that, remember these three here were menu 552. This time we're going to do menu 553. Menu 553. Menu 5, probability, 5 for distributions, and 3 for inverse normal. All right, the area, we want 0.95, and that gives you 1.64485 equals 1.64485. Now, if you look it up on the table, you're going to have to do a little extrapolating, and you get 1.645. Okay, and that's considered. Okay, and we'll just look on the table, and we got 90. So we're going to have to go down to the other page here, and we're going to look for 0.95, and you can see it's halfway between these two right here. So that's why they would say 1.645. Critical values. For the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. And we generally find them, they're usually over here in the tail somewhere, okay? And I say that they're defined a lot of times. And that's not about it. Generally, a lot of people use 95%, okay? And then, so this over here is 0.025, and this area over here is 0.025, okay? So if 95% of the data fall in, they generally consider this the not significant. And then over here would be low significance, low significance, I can't even spell significant, can I? And over here would be high. Okay, high. And then this would be 95%. So that's a. Now, what are these z values here? Well, we can go back to our tape or our calculator. Menu 553, and we find 0.025, and we get negative 1.95595. We're just going to say negative 1.96, okay? And then find this area here. Now remember, we got to add those two. So 0.025 plus 0.95 equals 0.975. Now, here's the really cool thing. Remember, this thing is symmetric. So this side over here is a mirror opposite of that. So if that's negative 1.96, this should be 1.96. Okay, so let's try that. Menu 553, 0.975, and let's see what we got. 1.95996. So 1.96. All right. So generally, if it falls in over here or if it falls in here, that is where it cuts off. Okay, that is the critical values. So a lot of times people use z equals plus or minus 1.96 to find those critical values. All right. Another one that they use is 0.01. Okay. All right. Sometimes you may see something like z, and then down here in the bottom you got, and that's the alpha symbol right there. This is called alpha, and you may see something like z 0.025. Okay, well, And this reads from the right, so it's a little bit different. It's 1 minus 0.025, which is 0.975, which would be 0.025 would be 1.96. All right, folks, great job. Enjoy your evening, and I'll see you in class tomorrow.